Alrighty, let's talk about Kepler's laws. It's a flu that's based on a swan on pigs, I believe. I believe so, yeah, probably a pig. Okay, so Newton's law of universal gravitation, which you've been introduced to already, which we will now sort of study a little bit more in depth, was actually based on the work of Johann Kepler. So Newton owes a lot of thanks to Kepler. Kepler in turn owes a lot of thanks to Brahe. There's Kepler there. You'll notice that many of the gentlemen of the age had a lot of traffic accidents. They wore the big neck braces. Yeah.
That was
terrible.
Yeah.
You need better jokes.
I like the rating number.
What was the deal with wearing those anyways? Like, did they actually think that was fashionable?
I guess.
There must have been a practical reason for it too, don't you think?
No.
No?
Just to show.
It works corsets. What's the practical reason for that?
Well, fair enough.
It's all about look.
Yeah.
Exactly. It makes them look.
You think people will laugh at our dress in 100 years?
Ew, they're still there.
Look at those jeans.
Jeans?
They're so casual.
All right. So, Kepler's three laws. His first law says, hey, you know what? Planets move in elliptical orbits with the sun at one focus.
Not a circle.
Not a circle, as commonly sort of thought. They actually move in elliptical orbits. Now, what is a focus? Pre-calculus people? What is a focus?
Point in the middle.
Do I have the picture? There it is there. Okay? So, here is the sun, right? And the planets move in an ellipse. The sun is at one focus. There's nothing at the other focus. Okay? So it's kind of like the two centers. Okay? Now, pre-calculus people might remember stuff like this, where it's like h minus k squared plus, no, is it x minus k squared? Or h? X? Yeah. X minus k squared and y minus, is it j?
It's h. It's h.
Oh, yeah. Squared, and that's like radius squared, right? Or something like that. Crazy sort of formula for the ellipse. The foci, which is plural for focus, the foci are those two sort of kind of the centers. You don't need to know that. All you need to know is that planets move in an elliptical orbit. Kepler's second law is a little bit more mathematical. He said that a line joining the sun and a planet will sweep out equal areas in equal times. Now, what the heck does that mean? Okay, and here's a little animation to show it. There's the sun. Now, this ellipse was extremely exaggerated there in that last picture. It's not actually that elliptical. So there's an example. We've got the sun at the center. We've got a planet orbiting it, right? He said that if you were to take those pie slices, like if you imagine every one of those pies to be like a month of equal length, of course, the area of that pizza slice would be the same.
Why is that? When the speed is the same, or is that?
Actually, the speed changes. It gets faster as it gets closer, and then as it goes out to the outer regions, it actually slows down, right? But the area is the same. So that's how you can predict sort of things that orbit, right?
Well, I wish the clock dies and you say no.
Now you might want to draw a picture that kind of looks like that. I don't know if that helps you to understand what's going on there. Obviously, it's hard to draw an animation. Okay. Triangles of all the areas of all the triangles are the same size. Now, Stefan's already answered my next question. This means that the planets must travel faster when it is near the sun and slower when farther away. Okay, because they must be equal times. So closer to the planet, or closer to the sun, faster up here, slower as they farther. And I think sort of intuitively people get that, right? And that has to do with gravity and whatnot. Yeah, good. Now the third one is sort of the big math one here, which is probably one of the most useless things that I teach, I think. The following ratio is the same for all planets or satellites which orbit around the same central body. Okay, so they must orbit the same object, and this ratio is the same, and it is r cubed over t squared. R cubed, radius of orbit, t is period. So Kepler's law says that the radius cubed divided by the period squared is the same for anything that. So in other words, all the planets that orbit the sun, my volatile sun, all have the same r cubed over t squared value. All the satellites that orbit the Earth, all the moons and not moons, the moon and other things that orbit the Earth, all have the same r cubed over t squared ratio. Okay, r is the radius of orbit. Now that could be measured in meters or astronomical units. Do you remember what 1 AU is equal to? R is radius.
Little r or big R?
Big R. What's 1 AU equal to? 1 Earth orbit radius is an astronomical unit. It's not commonly used, but it seems like such a big number it should be capitalized. T is the period. Oh, there it is there. 1 AU is the average radius of Earth orbit. About 1.49 times 10 to the 11 meters. That's all.
Not that much.
Actually, that number's on that table that I gave you. So don't worry about constants. Any constant that you'll need, I will give to you on test and exam on this unit. Because there's so many of them, I wouldn't expect you to jot them all down. Okay? But you should know what an AU is. Periods could be measured in seconds, could be measured in days, could be measured in anything. As long as it's the same kind of thing. It's a ratio, and so the units really don't matter. I'm not going to bother clicking there on astronomical units.
Click here.
I don't even remember what's there.
Well, there you go.
Probably a link to Wikipedia or something. I don't even know. You just need to know r cubed over t squared. Okay. Now, anything that orbits the sun, we list it as K sun.
What's a little something?
I don't know, it's just a note. K sun, so anything that orbits the sun has an r cubed over t squared value of 3.35 times 10 to the 18 cubic meters per second squared. Useless fact of the day. Eh? That one you should probably have. Yeah, meters cubed per second squared. Well, because it's a radius cubed, so it's meters cubed.
That's the rotation of the sun.
That is the ratio of radius to period for all objects orbiting the sun. If you were to take Earth's radius of orbit and divide by its period squared, 365.25 days, and then take Pluto's radius of orbit, way far out, and divide by it.
That's not some days.
Way far out,
Oh,
right? You get that value.
well, that's just-
All objects orbiting the sun have this ratio of radius cubed to period squared.
Perfect.
There you go.
Okay, maybe.
Did I give you the sound? I think, you know what, there's only two. Can I just sort of quickly show you how you would do these kind of questions? I'm not even sure I ran off. How fast in in square meters per second is an area being swept out by a line joining the Earth and the sun? So in other words, if you were to take a rope and attach it to the sun and the moon, or the Earth, right? Every second, how much area, how big of a pizza slice would you map out?
That's so hard.
Well, remember, the area per second is going to be area divided by time. Yeah, this is just an example of something I might ask. The total area. Now, here's the lousy thing, is that from time to time they switch from, it's an ellipse, no, it's a circle. It's an ellipse, no, it's a circle, right? It's so close to a circle that sometimes they just say, we'll treat it as a circle. Because if I ask you to find the area of an ellipse, it's kind of more challenging. So here's an example where I'm assuming it's a circle. So the area is pi r squared.
Are you using a big R?
I don't know. Sorry, dude. So I got pi r squared over t. The radius of Earth orbit basically this is just a way of me reminding you about, I'm going to use Joy's if I can. Do you have that handout with the tables on the back of it? Maybe Joy didn't have it.
I got
There it is there. That's it. That's the one. Okay. On the back of this handout here, you'll see all of the Earth orbits, mass of the planets, all those kind of things, right? So the orbit of Earth is 1.49 times 10 to the 11. We're going to square that because it's pi r squared. Where do you think 3.16 times 10 to the 7 comes from? Well, because we're going per second, this is equal to 365 and a quarter days times 24 hours in a day times 60 minutes times 60 seconds. It's going to give you that 3.16 times 10 to the 7. Okay? Do the math. You get an incredible area of 2.21 times 10 to the 15. Billions and billions of square meters per second.
That is so far away.
It makes your head hurt.
No.
We,
Always being 4 light years calling me.
yeah? I agree.
It doesn't make sense.
Yeah.
Does it make sense?
That makes sense, it's a real picture. There's just a picture of it.
Yeah. Just
Just
use
snap one, like just quick.
yeah, use an iPhone. It's like up a meter stick? Yeah, about 4 light years. I won't